In this lecture, we're going to look at elasticities. These are extremely important when we consider such things as how fast things are changing, how fast increases in prices will affect quantities, and to what extent. Recall that we were using a Cobb-Douglas production function. Well, the Cobb-Douglas, if you estimate the parameters on those kind of functions, you automatically get the elasticities. So let's get started on this. As you may have expected, the price elasticity of demand is simply a percentage change in the quantity demanded, Q, percentage change in Q, divided by the percentage change in price, also referred to as the demand elasticity. The formula for the demand elasticity, and we denote the demand elasticity or elasticity of demand by this epsilon, is given by epsilon is the percent change in quantity demanded divided by the percent change in price, and percent change is simply the change in Q divided by Q. So if we go from 1 to 2, it's basically 1 divided by 1. If we are looking at demand elasticity, it has to be negative because the demand function is downward sloping. So if the price elasticity of demand is -2, so if you have that Cobb-Douglas production function and you estimate the quantity as a function of price, and as a result estimate that price parameter p to the power is -2, that implies that a 1% decrease in price would cause quantity demanded to increase by 2%. A decrease causes price to increase. If a 1% increase in price occurs, quantity demanded would decrease by 2%. Now we can distinguish between an arc price elasticity of demand, so that means that we're looking at a little piece of the demand function, or a point price elasticity of demand. The arc price elasticity of demand is calculated using two distinct points, and we use the average price between those 2 points. So in the previous slide I pointed out that it goes from 1 to 2, and I used 1 as my, so the change in Q was 1, 2 minus 1, and then I used 1 as my denominator, but I should have used 1.5 instead, because 1.5 is the average of 1 and 2. So we use the average price and the average quantity in such a way that we get epsilon is the change in Q divided by the average Q over that range, divided by the change in price over the average price over that range. And we can rearrange that as delta Q over delta P, P bar over Q bar, where the bars indicate an average value. Then the point price elasticity of demand is simply evaluating the elasticity at a specific price quantity combination. So to calculate the point elasticity of demand, we rewrite the formula as epsilon is equal to delta Q over delta P, P over Q, which is less than 0 because delta Q over delta P, which is the slope of the demand function, okay, is less than 0. The calculus version of this is dq dp, P over Q. Now dq dp is not really the slope, right? It's the inverse of the slope. So we can think of this a little bit different when we write it in inverse demand functional form. So we work mainly with the linear demand function, and I prefer to write the linear demand function so that beta is positive and alpha is positive. So we have Q equals alpha minus beta P. Now some write it as in this way. My colleague at UBC writes it this way. I prefer this way here because he then has beta less than 0. When the parameter beta is less than 0, negative, then we write this as in this way. But otherwise, when I write it this way, I get delta Q over delta P equals dq dp, equals beta, and I then get epsilon equal to minus beta over minus beta times P over Q. But you always have to be aware of this, of the assumption that you make regarding whether beta is defined as being positive or negative. Again, be careful that you distinguish between the regular form of the demand function, namely this form, with its inverse form in this case, which is the correct form in terms of an XY graph. So here we have the inverse form, which is given as P, solving P in this equation, as alpha over beta minus 1 over beta Q. Using the inverse form could lead to an erroneous calculation of the demand elasticity, epsilon, if you're not careful. Now, an interesting case is if you have a horizontal demand function, which of course is the case if you're a price taker on a world market or something. So a horizontal demand function has the formula P equals alpha minus 0 times Q, so it's just P equals alpha. In regular form, this gives you alpha over 0, which you can't have, of course, minus 1 over 0, which you can't have. But if you let that go to, if you approach 0, then this becomes infinity, of course. So when calculating the demand elasticity, we get delta Q over delta P is equal to minus 1 over 0 divided by 0, which turns out to be actually negative infinity. So the horizontal curve is infinitely elastic at all points. So we just saw that the horizontal demand function is infinitely elastic. What happens if we look at the price elasticity for a vertical line? Well, now we get Q equals alpha minus 0P. Thus we have delta Q over delta P is equal to 0. So a vertical demand curve has a 0 price elasticity at all points. So if we write the demand function as a linear function, Q equals alpha minus beta P, the demand elasticity, epsilon, is given by minus beta P over Q. So it's negative. Since beta is constant, equal to the inverse of the slope of the demand curve, it is only P and Q that cause the elasticity to change as we move along the demand curve. So this is important when we're going to go and look at monopoly. Here we get the same function that we had before when it comes to avocados. You'll recall that this was 80 million pounds of avocado if the price was 2. The point here is that at this point where the demand function intersects the vertical axes, we get perfectly elastic demand. So in other words, the elasticity is minus infinity, the price elasticity of demand. Between that and this point here, the price elasticity is less than minus 1, and it's between 0 and minus 1. Pardon me, it's between 0 and greater than minus 1 if we are in this part of the function. And it's perfectly elastic, in other words, 0 at this point here. So moving up the curve, P gets larger and Q smaller, we get more elastic demand. Moving down the curve, P gets smaller and Q gets larger, so we get less elastic demand. Simply by the way that the equation works. Now there are other demand elasticities that we can look at. Let's assume that the demand function that we had there on the previous slide for avocados looks like this: 680 minus 4P plus 2PT, where PT is the price of tomatoes and a function of income of 0.01 times income. So P is the price of avocados, PT the price of tomatoes, I is consumer income. We can calculate the own price elasticity of demand, the income elasticity of demand, and the cross price elasticity of demand with respect to the price of tomatoes. So assume that the price of tomatoes is 80, income is 4,000, and P is 200. I'll give you some time to calculate each of those. The only change in the formula is that instead of using instead of using P, we use now changes in PT and changes in income, but the formula remains the same. We can see this by first looking at the income elasticity, which is the percent change in the quantity purchased given a 1% change in consumer income. Here's the formula. All right, in this case, we've called it E sub I. The elasticity with respect to income, it's delta Q over Q divided by delta I over I, which we rewrite as delta Q over delta I times I over Q. And we evaluate that, of course, at a specific point. So if we suppose this is the equation, the one we had on the previous slide, with PT80, I 4000, P200, we plug in values to get Q star equals 80. Clearly, delta Q over delta I is equal to 0.01, and thus we get, using the equation for income elasticity, 0.01 to 4,000, which is the income, and the price, the quantity here, Q is 80, and it's a half. So it's greater than 0, and therefore it's a normal good. We can also look at the cross price elasticity of demand, which helps determine whether we have a substitute or a complement. The cross price elasticity is simply the percent change in the quantity purchased given a 1% change in the price of the other good, in this case tomatoes. And it should have a capital T there and there, but I forgot to do that. So given the demand function from the previous slides, which Q star is 80, then we plug that in here. The change in Q divided by the change in the price of tomatoes is 2 from the previous slide, and as a result the elasticity with respect to the price of the other good, so the cross price elasticity given by these formulas, this formula here, we get 2 times 80 over 80, and we end up with a cross price elasticity of 2, which indicates that tomatoes are a substitute for avocado. Now the supply elasticity is a little bit more interesting in some ways, but it's the same kind of formula as the demand elasticity, the price elasticity of demand, and here we're looking at the price elasticity of supply. So the supply function we denote as Q equals A plus BP, and it's the elasticity of supply, which we denote by epsilon sub S, is equal to the percentage change in quantity demanded over the percentage change in price, delta Q over Q, delta P over P, which is then delta Q over delta P times P over Q, and it has to be positive because A and B and P and Q are all positive. So the elasticity of supply is either 0, and it could be less than 1, in which case we have inelastic supply elasticity. If it's 1, we get unitary elasticity, and if it's greater than 1, we have a elastic price elasticity with respect to supply. Finally, what makes things interesting is when it comes to demand, many economists have estimated demand functions for a large variety of goods and services and thereby determined their elasticities. They've tried to do that for supply as well, and one can get those supply elasticities. The problem with supply is that you can have it that when you estimate a supply function, that the intercept on the horizontal axis is positive, which means it's a little harder to calculate what the producer and surplus is going to be. Just think about it. If you take that supply curve, one of the ones drawn here that goes through the origin, if it's to the right and intersects that quantity axis to the right, then you have to subtract a piece, a triangle underneath the quantity curve from the producer surplus, or from the cost to get at the producer surplus. But often the best assumption that economists can make when they don't have much information about what the supply elasticity is to assume that the supply elasticity is equal to 1. Any supply curve, any linear supply curve that goes through the origin has to have an elasticity of 1. All right, so that both supply functions S1 and S2 originating through the origin have a supply elasticity of 1. It's easy to prove. Given Q is A plus B, P, ES is simply dQ over, the delta Q over delta P, the change in Q over the change in P, times P over Q. At point 0, so it goes through 0, we put Q minus, so whatever Q you have, subtract 0 from it. All right, so the change in Q over the change in P is given by Q over P only. I don't have this very clear. You have to see that there's a demarcation here. So it's Q minus 0 over P minus 0, which is Q over P, times P over Q. P over Q, and that's equal to 1 always. This is true for any P and Q, so that for any straight line supply function going through the origin, the supply elasticity is equal to 1.